MCP just received the biggest update since the protocol was introduced. And this is not a small feature release. The fundamental way MCP clients and servers communicate has been redesigned. Until now, a remote MCP server often behaved like a long-running conversation. The client connected, introduced itself, negotiated capabilities, received a session identifier, and then continued sending messages through that established session. That worked, but it also created one of MCP's biggest infrastructure problems. The server had to remember who the client was, what had already been negotiated, and which messages belonged to which session. Now, that is changing. With the July 28, 2026 specification, MCP is moving from a stateful, bidirectional protocol core toward a stateless request-response model. In practical terms, an MCP server no longer needs to remember an entire conversation just to process the next request. Every request can contain the information required to understand and process it. That might sound like a technical implementation detail, but it could completely change where MCP servers run, how easily they scale, and whether MCP becomes a specialized AI protocol or something closer to the HTTP layer of the agentic web. So what exactly changed? And does this deserve to be called MCP 2.0? To understand the update, we first need to look at the old model. Imagine an AI coding assistant connecting to an MCP server that exposes GitHub tools. Before the assistant can call a tool, the client and server establish an MCP session. The client sends an initialization request containing its protocol version, identity, and supported capabilities. The server responds with its own capabilities. The client then confirms that initialization is complete. After that, the server assumes that future messages arriving through that session belong to the same client and follow the capabilities that were already negotiated. This allows rich, bidirectional communication. The server can send notifications, request additional information, ask the model to generate something, or interact with the user through the client. But the infrastructure underneath becomes more complicated. If the first request reaches server instance A and the next request reaches server instance B may not know anything about the session. You can solve this with sticky sessions, which force the same client to keep reaching the same server. You can also use a shared session store that allows multiple instances to access the same state. But both solutions add complexity. They make serverless deployments harder, they make load balancing more complicated, and they make a simple MCP tool server behave more like a persistent application server than a normal HTTP endpoint. The new specification attacks that problem directly. In the new stateless model, each request is self-describing. Information, such as the protocol version and relevant client capabilities, can travel with the request itself. The server processes that request independently and does not need to infer context from an earlier initialization handshake. There is no requirement for the same client to reuse the same connection. There is no requirement for the next request to reach the same server process. And there is no MCP session identifier that every server instance must remember. One request can reach instance A, the next can reach instance B, a third can reach a temporary serverless function that disappears immediately after returning the response. As long as each instance understands the request, the system continues to work. This makes MCP look much more like an ordinary HTTP workload. You can place several MCP server instances behind a normal round-robin load balancer without forcing every client onto a specific machine. You can deploy an MCP endpoint as a serverless function. You can move execution closer to the user through edge platforms. And when traffic suddenly increases, the platform can create more instances without transferring an active MCP session into every new process. This is why the stateless change matters far beyond cleaner protocol design. It removes infrastructure friction. But MCP has not simply removed state and ignored all the interactive features that depended on it. Some operations require more than one exchange. A tool might need the user to approve an action, a server might need additional information, or an AI workflow might need the client to generate a model response before the original request can continue. For these cases, the specification introduces multi-round trip requests. Instead of relying on a permanent bidirectional session, the server can return an input required response containing requests that the client needs to handle. The client processes those requests and then retrieves the original operation with the new information. When temporary state must survive between those rounds, the server can return opaque request state that the client sends back during the next request. The important difference is that the client carries the state between rounds. The server does not need to store a live session in memory. This creates a stateless protocol without reducing MCP to one-shot tool calls. Another major part of the release is the formal extension framework. MCP's core is becoming smaller and more stable, while specialized capabilities can evolve as optional extensions. Two of the most important examples are MCP Apps and MCP Tasks. MCP apps allow servers to provide interactive user interfaces that can appear directly inside an MCP host. Instead of returning only text or raw structured data, a tool could return a chart, a form, a dashboard, or another interactive component. Imagine asking an AI assistant to analyze cloud spending. The server could return an interactive cost dashboard rather than describing every result in paragraphs. Because MCP apps use the extension framework, clients that support the feature can enable it, while simpler clients can continue using the core protocol. MCP tasks solve a different problem: operations that cannot finish inside a normal request. Some AI actions take seconds. Others might take several minutes or even hours. A large research job, video render, software deployment, data processing pipeline, or code-based migration should not require one HTTP connection to remain open until everything is finished. Tasks give these operations durable handles. The client can start a task, check its status later, provide additional input when required, and retrieve the result when the task is complete. So MCP can now support both extremes. Short requests can remain completely stateless. Long-running jobs can become durable tasks rather than fragile open connections. Authorization has also received significant attention. Remote MCP servers often sit between an AI application and sensitive services such as source code repositories, databases, cloud platforms, and company systems. That makes vague or incorrectly scoped access tokens extremely dangerous. The updated authorization model aligns more closely with modern OAuth and OpenID Connect deployments. MCP clients can discover the correct authorization server, request tokens for a specific MCP resource, and react when a server requires stronger or additional permissions. Servers must validate that an access token was actually issued for them rather than accepting a token intended for another service. The goal is to reduce token confusion, accidental credential sharing, and authorization flows that work in demos but become dangerous in production. There are also smaller changes with large operational consequences. MCP method and tool names can be exposed through HTTP headers, making it easier for gateways to route, authorize, rate limit, and observe requests without deeply inspecting the JSON RPC body. List results can include cache information, so clients do not need to repeatedly request the same tool, prompt, or resource definitions when nothing has changed. Together, these changes make MCP easier to place behind the infrastructure companies already use for ordinary APIs. So is this MCP 2.0? Officially, no. The specification is identified by its release date, 2026-07-28. But conceptually, the MCP 2.0 question is understandable. The protocol is changing from something that often behaves like a persistent AI connection into something that can operate as a scalable, stateless HTTP layer. For developers, this means simpler deployment, easier horizontal scaling, better compatibility with serverless and edge platforms, and clearer patterns for long-running work. It also means migration work. Existing servers that depend heavily on session state, initialization behavior, or permanent bidirectional connections may need architectural changes. Not every MCP server should immediately move to the edge, and stateless does not mean an application never stores state. Databases, tasks, user accounts, and external systems can still contain state. It means the MCP protocol itself no longer requires one server process to remember the history of every client connection. That distinction could be what allows MCP to scale beyond local developer tools. The original version showed that AI applications needed a standard way to connect with tools and data. This release focuses on what happens when millions of clients begin using that standard in production. MCP has not literally become the HTTP of AI, but with self-contained requests, ordinary load balancing, cacheable discovery, gateway-friendly routing, formal extensions, stronger authorization, and durable tasks, it is beginning to look much more like the infrastructure layer that could earn that title. The biggest problem with MCP may not be completely solved, but the protocol has just removed one of the largest obstacles standing between an interesting developer standard and a production-scale AI ecosystem. If you enjoyed this video and found it useful, leave a like and subscribe to the channel for more clear explanations of AI, software, and the technology changing how we build. Thanks for watching, and I'll see you in the next one.